Welcome back. We're going to begin Chapter 3 of the Energy Onion Energy Systems Engineering Certification. Keeping this chapter in context, you have already been through the introduction and lighting, and now we'll begin Chapter 3, HVAC and Thermal Energy Storage. Because HVAC is a technically complicated subject, we're going to benchmark some of the componentry, some of the functionalities that affect energy consumption with HVAC, heating, ventilation, and air conditioning. Some of these considerations are, of course, external climate, the building envelope, and potential for leakage, as well as solar heat gain through glazing, internal heat gain, particularly process heat gain. Fresh air and air changes affect the energy consumption. Places where control systems have simultaneous heating and cooling, or heating, humidification, cooling. Temperature and humidity requirements in a space. Of course, the set points affecting the energy consumption. The system type and hours of operation. The hours the space is occupied. Equipment efficiencies. The energy distribution requirements. System thermal losses, duct work, piping, and so forth. And of course, all of these things are affected by whether the equipment is in good condition or poor condition. So you see, the HVAC energy consumption picture is more than just finding a very efficient air conditioning system, heating system. There are considerations beyond just the equipment itself, its efficiency and condition. As Energy Onion's consistent perspective is to give you context, we try to begin every technical chapter with definitions. A boiler is simply a closed vessel in which fluid is heated. That's the simple definition. A furnace can be either direct or an indirect heating device. A heat pump, although it likely generates a thought in you of a specific type of heat pump, a heat pump, strictly speaking, is a device that moves heat from one location to another through mechanical work. That's an important definition because as you consider a geothermal heat pump or a heat pump on a home, they both do the same thing. They move heat. An air conditioner is a system designed to dehumidify and extract heat. Air handlers are devices used to condition and circulate air as part of an HVAC system. A chiller is a machine that removes heat from a liquid. That can be done either through vapor compression or absorption. We won't talk about these differences because this is an example of details left to the HVAC contractor. But we will present the functionality and the difference and the availability of those two types of heat removal systems. A heat exchanger is a device used to transfer heat from one medium to another. Typically, in a heat exchanger, those mediums are separated maybe by a copper wall and a pipe. But not always. There are wheel heat exchangers where two gases, or air and another gas, exchange heat and mix, but typically they're separated. A PTAC, be familiar with that abbreviation, is a packaged terminal air conditioner. It's self-contained air conditioner and usually has heating as well. You may be most familiar with these because in the U.S. they're most often used in a hotel room. The air conditioner sticking through the wall. An economizer is specifically a mechanical device used to reduce energy consumption. That's the definition. It can be used, for example, in different applications for a boiler or HVAC, For our purposes today, when we refer to an economizer, we're talking about an air side economizer or an HVAC economizer. In this configuration, an economizer is just pulling in outside air if the temperature and humidity of the outside air is low enough to cool an interior space without additional conditioning. The SEER, Seasonal Energy Efficiency Ratio, or EAR, Energy Efficiency Ratio, these are ratios of heat extracted to energy input. The SEER is a testing protocol that takes into account that most units experience their operation, in different seasons. Although we don't go into detail, the SEER testing protocols assume a certain kind of season. However, do indeed all locations have the same seasons? Is the season in London, or the seasonality in London, the same as the seasonality in Phoenix? The HSPF, or the Heating Seasonal Performance Factor, is the measure of a heat pump and its efficiency during heating. It's like a seasonal, it's a seasonal measurement like SEER, but it's a heat pump during a heating seasonal performance. Kilowatts per ton is a ratio of how many kilowatts are needed to generate a ton of cooling. As we'll be using this ton of cooling, let's define that as well. A ton of refrigeration is defined as the cooling power equivalent to 1 ton of ice melting in a 24-hour period. That's equal to 12,000 BTUs per hour, or 3,517 watts. The dry bulb, the wet bulb temperature. Dry bulb is just what you might consider the regular air temperature. Wet bulb, the way of measuring in technical definition is, it's if you had a wet sock around your thermometer and you spun it around to cool that wet sock through evaporation, the temperature inside would be a wet bulb temperature. Wet bulb takes into account humidity and evaporation. We'll see later that the intersection, if you have something called a psychrometric chart and you intersect wet and dry bulb temperatures, that's the relative humidity. That's why these are on the same line, dry bulb and wet bulb, is because of their interplay in calculating relative humidity. These last two definitions, latent heat and sensible heat. Latent heat is when you cool something or when you heat something, one of two things can happen. Let's take, for example, heating. When you heat water, you can increase the temperature of the water, but at some point, the liquid water will become gaseous water, water vapor. Sensible heat, think of sensible, sensation, sensing. That's a change in temperature. Sensible heat is the heat that changes the temperature of a thing. Latent heat is after the temperature has been changed and it begins this phase change from liquid to gas, from solid to liquid. Latent heat involves the change of phase. I mentioned earlier the psychrometric chart. Psychrometric chart is used for many calculations in HVAC. I'm going to illustrate one that I referred to a minute ago, and that's the relative humidity. As you notice across the horizontal axis are numbers that are referred to as the dry bulb temperature. This is the regular temperature. Let's say, for example, this is 25 degrees C, room temperature. And then let's say we had an apparatus that mimicked what I mentioned earlier, this wet sock. What's the temperature if you include evaporation? Well, indeed, if you include evaporation, the temperature will always be lower. The wet bulb temperature will be lower than the dry bulb temperature. You plot the wet bulb temperature, you see across the wet bulb or saturation temperature in the upper left corner of the graph. Draw a line where it says 15 degrees C. That intersection is the relative humidity, and it's 35% relative humidity. If it were drier, the wet bulb temperature would be colder. There would be more heat of evaporation. If it were more humid, the wet bulb temperature would be near the dry bulb. Indeed, if the dry bulb and wet bulb are the same, there is no evaporation of the wet in the wet sock. There's no evaporation because the relative humidity is already 100%. So that's a common use of a psychrometric chart. Another use of the psychrometric chart is if you have an apparatus, which you don't use a twirling wet sock anymore, you have an instrument that measures relative humidity. But if you were to measure temperature and relative humidity, this box is considered the comfort zone. Outside of this box, most people will be uncomfortable. Certainly you pick any point in this box and not everybody is comfortable. But outside of this box, most people will be uncomfortable. And inside this box you go from 20% to 80% relative humidity and from 20 to 27 degrees C. We're presenting here a refrigeration cycle, and strictly speaking, this is vapor compression refrigeration. We mentioned earlier vapor compression versus absorption. Later we'll discuss absorption, but this is vapor compression refrigeration. Let's look through four mechanical components of a vapor compression refrigeration cycle. One is the compressor, that which takes a low pressure gas and compresses it into a high pressure gas. The next component, the condenser, condenses high pressure gas into a high pressure liquid. In this, the heat is transferred from the refrigerant to something else. The heat leaves, condensing the gas. The next component is an expansion valve. The expansion valve converts a high pressure liquid into a low pressure liquid, and that expansion makes this low pressure liquid cold. Then going through the evaporator, you have a cold liquid which can accept heat from the inside air at the evaporator, and the evaporator rounds out the four components of a vapor compression refrigeration cycle. You see the difference in color, hot and cold, red and blue. You see a high pressure side, a low pressure side. It's important that you understand this picture. You may have heard it said that understanding something that is simple, understanding it well, is better than understanding poorly something that's more complicated. And that's the case here. This is a simplification of refrigeration, but if you understand it well, you'll be better off than somebody who doesn't really understand the more complicated picture. Like the diagram of an electric motor will be central to several areas of energy efficiency and power generation, renewables, the refrigeration cycle is central to air conditioning, chillers, heat pumps. The question being, how do you extract heat from some medium? There are a couple broad categories that we'll use now to divide HVAC systems into two types. You can consider a decentralized HVAC system, including window air conditioners, PTACs, self-contained air handlers, and some special units. The similarity here is that the heating, cooling, the ventilation, whatever it is that's happening is happening local to the space where it's needed. Contrast that with a centralized system of air handling and distribution. The conditioning of the air may occur locally, but the heat generation or cold water, whatever it is that is used to condition the air, is located in a central plant, maybe a boiler providing hot water or a chiller providing cold water. This centralized system of air handling and distribution will provide a complexity in configuration of zones, the constant versus variable volume. You have ducts and 2, 3, 4 pipe systems to consider. And in some cases you may condition the air to reduce humidity, but then need to reheat it because removing humidity cooled the air too much. As we survey HVAC systems, we'll look for some system goals, we'll consider some systemic problems, and then some problems that are more related to the zone, location, or zone type. First is the goals of sensible heating and cooling. As we discussed, sensible, sensing, the sensation is the felt temperature change. Heating and cooling. We'll look for humidification and dehumidification. That would be latent. Again, phase change if you're humidifying and dehumidifying. We'll look then at ventilation, the pressurization, meaning if, say for example, a door was open, would air in that building blow out the door, or would the air be sucked in through the door? Is the building positively or negatively pressurized? We'll consider outside air makeup. In some respects, to achieve a building code requirement of a certain amount of outside air. When you survey the system goals for HVAC, you also have to include air filtration. And then lastly, the regulation and automation of the system. What are some of the systemic problems you can have? You can have problems with your equipment. You can have problems with ducts or pipes, ducts being what move the air, pipes being what move the liquid. You could have leakage in the duct or the pipe. You could have negative pressure. We talked about pressurization as a goal. It is not a goal to have an uncontrolled negative pressure where your building pulls air in from the outside other than the intended outside air makeup. Zoning problems you could have are by elevation. Consider whether you would have a different zoning problem during the heating season on the north elevation, the south elevation, the east, or the west. You can also have zoning problems by perimeter or interior. Consider just one elevation, maybe the west. Western elevation in Phoenix in the afternoon has a substantial solar heat gain. How would that differ on the perimeter of the building versus the interior shaded portion of the building? Let's consider an unintended system consequence when you achieve energy conservation in your operation or in your customer's operation through lighting retrofit, the ECM interaction. The energy conservation measure of lighting retrofit. If you replace incandescent lighting with lights that are more efficient, likely they convert less of the energy into heat. You now have lighting that generates less heat. During a cooling cycle, that's a benefit. During a heating cycle, that's a disadvantage. Waste heat removal. Waste heat is often used for other HVAC purposes or even other manufacturing processes. If you have more efficient equipment that produces less waste heat, that heat then needs to be created somewhere. Often chilled water is colder than it needs to be to remove the heat load, and you can increase chilled water temperature. That'll save you energy. However, as you saw on the psychrometric chart, increased chilled water temperature can increase dew point, and it can reduce humidification. You may now have an increased HVAC load because of increased humidity. And then the ECM of an air economizer. Often airflow is higher in economy mode and can cause pressurization problems. The relative humidity can swing back and forth inside as easily as it does outside. That can cause problems with people sensitive to humidity, arthritic, and it can cause problems with equipment. And lastly, one of the ECMs that is the most easily implemented is just turning off thermostats. If you're in a space that doesn't need to be heated or cooled and you turn off the thermostat, that can cause pipes to freeze at the perimeter because of lack of load. So here is just a snapshot of other energy conservation measures that can have an interaction, an interactive effect in HVAC. As we discussed system types earlier, we broke into decentralized versus centralized system types. Under centralized, we had considerations including, first, the zones, the number of zones, and second, constant volume versus variable volume. Let's look at single versus multiple zones first. Starting with the yellow boxes, both this single zone at the top and multi-zone at the bottom have exhaust air. Air that comes through the return plenum but is not brought back into the supply air, it's exhausted. Outside air, in a nice tight system, the outside air and the exhaust air should be the same in CFM, cubic feet per minute. And both of these systems also have outside air. Return air is the air that comes back from the conditioned space. And what you notice the difference here in supply air is a single zone has one supply duct, multi-zone has two supply ducts. Note, however, that the multi-zone solution still has heating coil and cooling coils centralized near the fan. Each zone with its own duct mixes using the mixing dampers heated and or cooled air to provide the right air condition for that space. Strictly speaking, and easily seen from this picture, in a multi-zone, the number of zones refers to the number of supply air ducts. You can notice here that a single zone is more efficient typically than a multi-zone, and the C and V on this slide is for constant or variable air volume, which we haven't covered yet, but you see single zone is typically more efficient than a multi-zone because you're not trying to control two zones air temperature from one combination of heating coils. In this configuration, either single or multi-zone, the air temperature set point in the space is achieved through controlling heating and cooling coils and then their flow of water and the temperature of the water. The next example changes the amount of air supplied to a zone, the so-called variable volume, variable air volume, VAV. So what you'll notice in the constant versus variable air volume is some similarities first, and that is exhaust air, outside air, return air, and supply air look all to be the same legs coming out of this central system. There's a difference on the VAV system, and that is the terminal units have the ability to adjust the air volume to different spaces in order to maintain the set point in that space. This ability to adjust air volume but create just one temperature of supply air does offer energy savings. That's why you see the variable air volume in either single or multi-zone as a more efficient control system than a constant air volume. The last ducting configuration we'll present is the less used dual duct system, where each space has two supply ducts, hot and cold. Let's look at the similarities. Although the system on the bottom, the words for exhaust and return don't show up, you see the yellow and green boxes and the purple boxes. Both of these systems have a single exhaust, a single outside air makeup, and a single return air. But similarly, they both have two ducts. So if you see two ducts coming out of the air handler, is it a dual duct system? Well, you need to look a little more closely. Note the top figure. You've seen this before. This is not a dual duct system. This is a multi-zone system. The difference is, in multi-zone, the two ducts each carry air that has been conditioned by hot and or cold coils and a mixing damper to control the temperature. In a dual duct system, each area, each space has a supply duct for cold air and a supply duct for hot air. So let's look then now at the last centralized HVAC configuration consideration. That is the number of pipes and this reheating issue. Let's consider the number of pipes and reheat. First, with the configuration of pipes being 2, 3, or 4. And what does that mean? In a two-pipe system, these are the number of pipes that are going to the coil that is exchanging energy with the air. The pipes that supply water to the coil that has a heat transfer with the air. That coil can have coming to it 2 pipes, 3 pipes, or 4 pipes. On the two-pipe system, that's one supply and one return. Say, for example, hot water comes in, it exchanges energy with the air, delivers heat to the air, and then less hot water, warm water, comes out. 2 pipes. In a 3-pipe system, both hot and cold water can come into the coil that exchanges heat or energy with the air, but then after the coil, those water streams are mixed into a tepid water. So you have 3 pipes, 2 in, 1 out. Terribly inefficient. Then there's a 4-pipe system that has 2 supplies and 2 returns. If you have hot and cold water coming into a coil, and then the hot water that is less hot and the cold water that is less cold stays in its own hot or cold pipe, you'll have less reheat or less cooling to do. What about the example here on the right of reheat? Note on the VAV system that we looked at before, there was only a cooling coil. This is a 2-pipe system. Therefore, with just a cooling coil, there's no way to reheat the room. Let's say the room is too cold, you can't heat it. Reheat is used as an efficient way to offer a little bit of heat without having to have that capacity of a hot water coil to the whole building. We've now looked at the different ways of distributing the air, the different ways of distributing the water reheating spaces that only have cooling coils. What about the distribution energy consumption? The fans, the pumps, auxiliary equipment that's used to distribute air, distribute water, it can be up to half of your building's energy usage. Some sample calculations that you can use here to determine fan horsepower, or given fan horsepower to determine something else. Fan horsepower is cubic feet per minute times static pressure. Of course, duct size will have a lot to do with static pressure, divided by a set of efficiencies: the fan, the drive, the motor. From this first equation, you can see where variable air volume has a tremendous advantage. Static pressure being what it is for a duct system. If you can reduce CFM, reduce fan horsepower, well, look at the equation on the bottom. Kilowatt hours is a function of horsepower. Likewise for pumping, if you can reduce the flow, the gallons per minute on a pump, you can reduce pump horsepower. And how would you do that? Well, if you don't need as much cold air supply to your ducts, let's say the cold water you're supplying to a coil comes back out and it's still really cold. You can do one of two things. You can reduce the temperature of that cold water and save energy if it's colder than it needs to be. Or you can reduce the flow of that cold water and it'll come out of that coil a little warmer. Balancing the flow and temperature of the water in your centralized system is where you find a tremendous energy saving benefit. Although during the definitions we defined a heat pump as anything that moves heat from one medium to another, let's consider now not the geothermal heat pump, but what we normally mean when we say heat pump. In HVAC, it's a reverse cycle heat pump that has the ability to be used as a heater or as a cooler. If you look at these red circles and compare it to the refrigeration cycle in the lower right, you'll see there is a compressor, a condenser outside, an expansion valve, and an evaporator inside. But this is the heat pump in a cooling cycle. Its ability to be operated in a heating cycle makes it unique. If you reverse the flow in the heating cycle, you get to see in a heat pump, the outdoor coil isn't always acting as a condenser or as an evaporator. It depends on which direction the fluid is flowing. As you looked at the previous picture of a heat pump, you saw a fan inside and a fan outside. Here you see more fans. The purpose of these fans is to draw air across the heating coil, across the cooling coil, draw fresh air. It provides the air movement. Note that the air handler is also referred to at times as a fan coil. So you'll probably hear that terminology. But let's look at some components. What are these components highlighted with the green ovals, these three? These are dampers, followed by this green pleated mechanism is an air filter. You have a heating coil and a cooling coil. In this example, you have two fans and thermocouples. Any one of these components you'll see as an opportunity for energy savings. In addition to proper equipment selection and settings and operation improving energy efficiency, look at the air flow and see how the air handler settings can dramatically improve indoor air quality. Speaking of fresh air and indoor air quality, I mentioned earlier this air handler does not have an economizer. What would it look like if it did? The economizer, also known as an air side economizer. If you have a cooling capacity of 7.5 tons or more, it's just a rule of thumb, but you can take advantage of cool weather to cool your building. For example, office buildings often are in cooling mode when the temperature outside is much colder than inside. And the reason is the load inside, the people, the lights, and the computers continually increase the temperature inside. Make a side note, however, if the outdoor air is cool but humid, you may still have to dehumidify it, which would mitigate your savings. The purpose of the economizer, drawing in cool outside air, is just like leaving the windows open in your house. So let's look at these red circles, 1, 2, and 3. In an economizing control strategy, which of these dampers could you afford to leave open? 1, 2, 3, multiple? Well, the answer is 1 and 3. And which could you afford to close a little? You could close 2 a little if you like. Say, for example, if 1 and 3 were wide open and 2 was closed, you'd have a 100% fresh air. If that meets your temperature control set points, then you can do that. If you are getting too cold, then you would want to damper down the exhaust and open up damper number 2. In the previous couple slides on air handlers, there were heating coils, cooling coils. We've talked generally about the manufacturing and control of air temperature is through the use of heating coils and cooling coils. But where does the hot water come from for this heating coil? And where does the cold water come from for this cooling coil? That's our next topic. Let's start with where the hot water comes from. A boiler. A boiler can be used to make hot water, steam, both. And there are a couple boiler types we'll look at in a minute. But the hot water created by a boiler is pumped to the heating coil and used to impart heat to the air that passes over it. The boiler types, just taking a minute to show these configurations, I believe will improve your conversational ability when the context turns to boilers, but also plant a couple graphic differences. Whenever there's something I can share with you quickly and easily that I think you'll take with you, I'll try to share it with you. And here's an example. The example is the difference between a water tube boiler and a fire tube boiler. A water tube boiler, are you ready for this? The water is in the tubes. In a fire tube boiler, the fire is in the tubes. Simple understanding of the boiler functionality so that when the context of the conversation turns to boilers, whether it's water tube or fire tube, won't trip you up. You know the definition. It's easy to see and easy to remember. Now there is a lot of simplification going on here. We didn't put superheaters, feed water, condensate, safety valve. These are meant just to show you the basic difference between water tube boilers and fire tube boilers. Again, in both, boilers are used to produce hot water and steam for domestic purposes, for processed water purposes, and as we came into this topic, to generate hot water for your HVAC heating coil. Moving away from boilers now, let's look at how we create cold water, chillers. Like a boiler is used to heat water for the air handler, a chiller is used to cool water for the air handler and other process uses. In this section, we're not going to go into refrigerant type, like DX, direct exchange, or water, or ammonia. And we're not going to go into the method of heat rejection. Is the heat generated from the compression cycle rejected to air, rejected to water. And we're not going to go into chiller type. Is it centrifugal? Is it absorption? Because it's beyond the scope. For our purposes, suffice it to say the basic functionality of a chilled water system is to make water or another fluid really cold and send it to the cooling coil. That's our purpose for a chiller. And then to reject the heat created during a refrigeration cycle to the air. And that brings up these four pictures. Starting with the two pictures on the left. The top left is an air-cooled chiller. The bottom left is a water-cooled chiller. Two different cooling tower representations are a natural draft or a fan-powered cooling tower. The next slide is a little more graphic representation of a typical chilled water system, and we will camp out and look at the detail of chiller and cooling tower components of a chilled water system. Discussing the differences between chiller types, we'll start with first a rule of thumb, a selection based on the stratification created as you consider chillers of different tonnages. We're not going to think about absorption chillers yet, and you'll note for the other four chiller types, the refrigeration cycle is still in play. The refrigeration cycle we looked at before and saw again in heat pumps. What we're looking at here is just the type of compressor. Remember the compressor component of the refrigeration cycle. Whereas reciprocating chillers are rumored to be going out of favor because of the comparable efficiency from cheaper solutions, the other three predominantly share the market based on capacity, based on this stratification. The first is in a small 10 to 100 ton application. The scroll compressor, also known as a scroll chiller, predominates. In the medium size, 100 to 500 tons, the screw compressor, or screw chiller as it's called, predominates. When you're looking at large systems, 300, 500, 5,000 tons or more, you're typically looking at a centrifugal chiller. And then some of the other considerations we looked at before, that you can have air cooling or water cooling, the heat generated by the refrigeration cycle. And indeed, in a specific or in a unitary chiller, you can have single or multiple compressors. And now for most of this chapter, I've been saying we'll talk about absorption later. Well, later has finally come. Let's look at the absorption chiller. The unique quality or characteristic of an absorption chiller is that it uses heat to provide cooling. How does this happen? The basic difference between what we saw before, electric chillers, and here an absorption chiller, is that an electric chiller uses an electric motor to operate a compressor. What's the purpose of a compressor in a refrigeration cycle? It raises the pressure of refrigerant vapors, which is different than an absorption chiller. An absorption chiller uses heat. The heat compresses the refrigerant vapors to a high pressure. Therefore, the rejected heat from power generation equipment, turbines, microturbines, engines, can be used with an absorption chiller to generate cooling. Now, you will rarely, probably never find an application where it is efficient to create heat to run an absorption chiller, but they're a good use of waste heat. So how do they work? In the absorption cycle, the low-pressure refrigerant vapor is absorbed into the absorbent, which releases a lot of heat. The liquid refrigerant absorbent solution is now pumped to a high operating pressure generator. And that uses significantly less electricity than that for compressing the refrigerant for an electric chiller. Now, when the heat is added at the high pressure generator from some excess or waste heat source, the added heat causes the refrigerant to desorb from the absorbent and vaporize. The refrigerant vapors flow to a condenser. At the condenser, the heat is rejected and it condenses to a high pressure liquid, just like in the refrigeration cycle. The liquid is then put through, yes, an expansion valve to the lower pressure in the evaporator, where it then evaporates, absorbing heat from the air, providing cooling. The remaining liquid absorbent in the generator passes through a valve, pressure is reduced, and then recombined with these now low pressure refrigerant vapors that return from the evaporator, and the cycle is repeated. So you understand why we wait to discuss absorption chillers. They're an interesting technical detour, but we don't want to present them as equal in their use or functionality or efficiency with the other chiller types. The purpose of this slide is really to test what you know now and to test what you should know as an energy systems engineer. And that is, locate on this picture the cooling towers. Locate the chillers. Locate the boilers, the chilled water pumps, the condensing water pumps. These are things that you'll become familiar with as you adventure into the work of an energy systems engineer. In addition to HVAC systems that we've discussed providing heating and cooling, there are occasionally distributed and local representations of other heating methods. The examples in this case are radiant or convective heating, and they can be in the floor, the wall, the ceiling. Convection heating can be naturally convective, hot air rises, or it can be forced air convection, just using a fan blowing on a hot surface or a fan blowing hot air into a space. But these are indeed common heating methods that can be more distributed and more local to a space. We introduced the term economizer to mean either an air side or water side economizer. Air side being utilizing cool, dry air from outdoors, bringing it into your space to cool the space without conditioning. A water side economizer utilizes the existing chilled water system, but in a new and interesting way. With the two loops, condenser water and chilled water, still being separate, but connected through a heat exchanger. You can take condenser water, cool condenser water, run it through your cooling tower, and cool it even more. And then through the plate and frame heat exchanger, draw heat out of the chilled water that's come through the building and send cool water back through the building. So you see from this EPA diagram that these two water circuits are in contact through the heat exchanger, and the only thing that is providing cooling to the water that goes into the building is the operation of the cooling tower and taking advantage of that latent heat of vaporization. It's worth a minute to take a pause here and see how the cooling tower works and what it does. We'll focus in a minute on the water balance in the cooling tower. But now just look at the diagram and see the air blown upward. You see that the cooling tower, this one pulls air up through a fan, and in a counter current, warm water is sprayed down onto that air. That warm water interacting the air causes water to evaporate. When water evaporates, the remaining water is cooler. Let's look at the water balance in the cooling tower as we prepare ourselves to look at chemical treatments. What you see here in the boxes are the ways that water can get out of the system. Water can get out through leaks. Certainly these huge mechanical systems can have some leaks. Water can get out through blowdown, and that is as the water is reused in a cooling tower and it becomes too saturated with the hardness in the water or the corrosive elements in the water, it needs to be removed. It can also evaporate, which is the primary function of the cooling tower, the evaporation of water. But then through that powerful fan, there is something also called drift. And drift is just droplets of water, not water vapor in evaporation, but droplets of water being carried out in this turbulent stream of air. The next two slides will illustrate the damage to equipment if either there is no water treatment or if the water treatment is insufficient to remove the hardness and scale and rust and corrosion causing elements in the water. This picture is of the fouling of water pipes, and these next two pictures are pictures of what's called the fill. This is around the perimeter typically of a cooling tower, and as that fan blows the air up, the air comes in through the sides. So this is typically where the water would trickle down in these plates and the air would contact it in these plates. And you see two fouling elements here. One is you see the algae, brown and green algae. You also see hardness and scale. You see rust. You see all sorts of things. But in this next picture, this is another element used to keep the water inside the cooling tower, and this is nearly plugged with calcium carbonate. As the number of zones increases, remember we talked about centralized or decentralized? Well, as the number of zones increases and you become more and more decentralized and the potential desired settings vary widely, not in an office space where maybe 68 is comfortable for one person but 70 for another, but in, say, a hotel where you might have 65 in one room, 65 degrees Fahrenheit, but it might be off in the next room. As this happens, it can make sense to install package terminal air conditioners, PTACs, rather than hot and cold centralized water systems. Like a window air conditioning unit, however, they can be quite inefficient. For example, if you have, say, 1,000 rooms and you're at 85% occupancy year-round, this is not unheard of for some tourist places. It's probably cheaper to install boilers, chillers, hot, cold water. However, if your hotel is 75% occupied Monday and Friday, 50% Tuesday, Wednesday, Thursday, 20% on Saturday and Sunday, then a PTAC is probably a better solution for you. Some of the components of a PTAC include, of course, a compressor. You still have to have a refrigeration cycle in this little component. There's a fan, a heat sink. It's like an outdoor unit except the compressor sits next to the coil instead of inside of it. And they often include as well an electric heat for reheating in the case that the air outside is too cool. We have now a couple slides on thermal energy storage. Something to consider right off the bat is why thermal energy storage. Thermal energy storage does not save in energy consumption. If you were to create cold water, store it in this big brown tank in the picture, and then use it later, it did not save in energy consumption. What it did save, or what it is likely to have saved, is in demand charges. Whereas the consumption of energy, kilowatt hours, as we discussed in our first chapter and in lighting, kilowatt hours of consumption is more like your odometer. How far have you come this month in your energy consumption? Your demand, however, is more like your speedometer. What's the fastest you've gone this month? What is the instantaneous maximum kilowatts this month? If you have spikes because of air conditioning and peak time and demand charges, it can be economically beneficial to reduce those spikes. Again, you're not changing consumption. You're just saying, you know what, I will chill my water at another time, at a time where I'm not in a demand cycle. So thermal energy storage works with either cooling or with heating. In cooling, you can make ice. Literally, the thermal energy storage has the capability of making and shaking the ice off and making more ice and making a huge container of ice and water mixed. You can just cool the water until the water's cold but not frozen. And you can use something called a eutectic salt that can get you colder than ice can and give you more heat transfer per pound than ice can. You can also use thermal energy storage for heating. Two ways: you can heat water just like you chill water, or you can have a thermal mass. Consider all of the blacktop roads are a thermal mass, thermal energy heating storage container. They absorb heat all day and emit it at night. So thermal energy storage, when it makes sense, is when you have demand charges, and it can take the form of either heating or cooling. The last component of HVAC could probably have been left out, but like, for example, the definitions of HID ballasts, we're going to give you examples of this so that when you consider HVAC, you will consider humidification or dehumidification. It is an important component of that comfort quadrant on the psychrometric chart. It's not just temperature, it's temperature and humidity. So enough introduction. Humidification can take the form of atomization. Atomization can just be using compressed air to blast a small mist of water into an airstream. Steam injection is just injecting steam into the air systems. An infrared pan system, you can have water in a reflective pan with the heat lamp over it. The water evaporates into the airstream passing above the pan. You can have evaporative pads. Evaporative pads are very common in a home for a humidifier. It's just a pad that wicks up the water and then the air flows through that pad. Or ultrasonic. In ultrasonic, the humidifier creates a high-frequency mechanical oscillation in a body of water. The water tries to follow that high-frequency oscillation. It tries to just go with the flow, as you will, but it can't because the water has such a high mass and inertia. So for just a moment, a vacuum is created on a negative oscillation as one oscillation pulls against the other, and it causes the water to cavitate into a vapor. Well, we could have used several slides as a summary for HVAC, but because of HVAC's technical nature and because of the breadth of topics we've introduced, I've chosen to summarize using the definitions. Again, the definition of a boiler is a closed vessel in which a fluid is heated. Maybe now you have more context of a boiler. A furnace can be either an indirect or direct heating device. You've seen an example of a heat pump. air conditioning, air handlers, chillers. You've seen a heat exchanger. Do you remember seeing that in the water side economizer? You've seen a PTAC, water and air side economizers. We haven't used the definitions of SEER and EAR, but you have those definitions to maintain in context. They're a rating for efficiency. Likewise, COP and HSPF, kilowatts per ton, terms that illustrate the efficiency and effectiveness of a particular unit. We used dry and wet bulb temperature in our psychrometric charting, and we considered latent heat in a cooling tower, latent heat of vaporization, and we considered sensible heat when we discussed the HVAC system. Let's move on now to the next chapter, building envelope.